This is a story about a guy named Joe. Joseph Weber, technically. He liked physics, aluminum, and doing things that most people thought were pointless, which makes him kind of a legend, but not the kind that gets a statue. He gets a Wikipedia page with a cautionary tone. Weber believed that space could ring like a bell, and that he could hear it. And he wasn't entirely wrong, but also he was very wrong. In the mid-20th century, physics was doing pretty well. We had nuclear bombs, nuclear medicine, and people who used the word nuclear in board meetings without irony. Everyone was busy splitting atoms, chasing particles, or arguing about Copenhagen. Joe was not doing that. He was thinking about ripples in space-time. This was not a particularly fashionable thing to think about because even though Einstein had predicted gravitational waves in 1916, no one had ever seen them, or heard them, or measured them, or even agreed whether they were real. It was, at best, a ghost story for physicists, and at worst, it was math with no consequences, which is the scariest kind of math. Let's back up for a second. Einstein. A man whose name echoes beyond the field of science. There simply was no one else of his caliber in his era. In fact, when Einstein was born, the most famous physicist was probably Lord Kelvin. Kelvin thought that physics was basically finished. He believed that all that was left was measuring things more precisely. And then Einstein showed up in a patent office with math that turned space and time into soup. In 1905, Einstein published 4 papers. They were all kind of ridiculous. One was about light behaving like particles, known as a photoelectric effect, leading to his own Nobel Prize. One was about the existence of atoms and Brownian motion. One introduced special relativity, and the last one contained the small, completely insignificant formula E equals mc squared. This was the Annus Mirabilis, or in English, the miracle year. Einstein was 26, he had no PhD, and the only people reading his work were a couple of physicists and his boss at the patent office. But those papers quietly broke the laws of physics, or at least rewrote them in ways that made Newton roll over in his metaphorical grave. Einstein started special relativity with a simple question. What if the speed of light is always the same, no matter how fast you're moving? Beautiful question and a weird question, and not one that Einstein came up on his own. To understand why anyone would even think to ask that, we have to rewind another 20 years, back to an experiment so famous it's mostly known for not working. This is Albert Michelson and Edward Morley. They were trying to solve a problem that most people today don't even know existed. It was called the luminiferous aether. And no, that's not just a Minecraft mod. It was a real thing that scientists believed in very seriously. Here's the idea. Light is a wave. Waves need something to travel through. Sound needs air, ocean waves need water, so light must need something too. That something, they said, was the aether. It was invisible, undetectable, it filled all of space and let light do its thing. Seemed illogical until they tried to prove it. So Michelson and Morley built this contraption, known as an interferometer. Let's show a more clear diagram. It's a little machine that splits a beam of light, sends it in 2 directions, and brings it back together. If the light beam takes slightly different amounts of time to return, they'll create an interference pattern, kind of like if you drop 2 pebbles in a pond and the ripples overlap. Sometimes they cancel out, sometimes they reinforce each other. The pattern tells you if one ripple got there first. Here's the plan. If Earth is moving through the aether, then the speed of light should be affected by that motion, like running into the wind or paddling a canoe upstream. Light moving along Earth's direction of motion should travel at a different speed than light moving across it. All Michelson and Morley had to do was prove that their interferometer in one direction and then rotate it. If the aether was real, the interference pattern would shift. Light would travel faster with the aether, slower against it. That was the plan. But the pattern didn't shift. Not at all. They tried again and again. No shift, no aether wind, no change in the speed of light. The experiment was supposed to prove that the aether existed, but it did the opposite. The result was confusing. So confusing that no one really knew what to do with it. They didn't throw out the ether, they just came up with weird ideas to explain why they couldn't detect it. Some said the apparatus contracted when it moved, others blamed the clocks or the calibration, or the ether was just shy. Physicists were basically saying, okay, the thing we're trying to measure is undetectable, but trust us, it's still there. This went on for a while. And then Einstein entered the conversation. He looked at the Michelson-Morley result and said, what if the speed of light doesn't change? What if the problem isn't the ether? What if the problem is how we think time and space work? That idea would have sounded completely ridiculous, except it made the math work, and it made the Michelson-Morley result make sense. If the speed of light is constant, then everything has to bend to make that true. Time, space, motion itself. Einstein called it special relativity. It said if you move really fast, time moves slower for you. Your length contracts, mass increases, and energy and mass are interchangeable. And light doesn't care how fast you're moving, it always moves at the same speed. Always. The Michelson-Morley experiment wasn't a failure. It was the first clue that the universe is a lot stranger than we initially thought. After 300 years of Newtonian mechanics, relativity shattered the illusion of absolute time. There was no cosmic clock, there was no universal now, no ether, just space-time. Einstein had solved a puzzle that most physicists didn't even realize was missing a piece. In 1923, Michelson won the Nobel Prize for a null result, for proving that light didn't behave the way people thought it should. That's the thing about physics. Sometimes the best discoveries are the ones that tell you nothing. But that nothing changes everything. Einstein took what Michelson and Morley couldn't find and turned it into the foundation for everything that followed. He threw out the ether, kept the constant speed of light, and let the rest of reality do the bending. No cosmic wind, no invisible medium, just light moving exactly the same for everyone no matter what. And if that was true, then space and time couldn't be what we thought they were. This leads to more weird stuff. As mentioned, time moves slower the faster you go, distances shrink, mass increases. The universe basically says the speed of light is sacred and everything else can adjust. That idea became the bedrock of modern physics, but it had one glaring limitation. It didn't include gravity. And gravity, inconveniently, is everywhere. Now, Newton had gravity handled pretty well back in the 1600s. He said things attract each other, the bigger the mass, the stronger the pull. It worked great. It explained falling apples, the moon orbits, and why you stay anchored to your chair while you watch this video. But Newton had a problem. His gravity acted instantly, across empty space. It didn't care about distance or time. One mass moved and the other just knew. That bugged Einstein. He thought gravity needed to follow the same rules as everything else, especially light. There were many problems with the idea of Newtonian gravity. First, let's talk about Mercury, the smallest planet in the solar system and the fastest one. And the only one that knew something we didn't. Mercury's orbit had a secret. It was telling us something was wrong. For a while, no one wanted to listen. Here's the thing about orbits. They're not perfect circles. They're ellipses, squashed ovals defined by gravity and momentum. And sometimes those ellipses shift. Not a lot, just a little rotation with each orbit. It's called precession. It's normal and all planets do it. But Mercury did it wrong. In the 1800s, astronomers tracked Mercury with alarming precision, and what they found was that Mercury was precessing its orbit faster than it should have, by 43 arcseconds per century. Not degrees, not minutes, arcseconds. That's 0.000012 degrees. Tiny, utterly microscopic, but real and unaccounted for. They tried everything. They added the gravitational pulls of every known planet, they adjusted the math, they blamed the sun's shape. They even invented a planet that didn't exist, Vulcan they called it, supposedly orbiting even closer to the sun, tugging subtly on Mercury. So they searched for Vulcan for decades, but they never found it because it wasn't there. Then came Einstein with a different idea, not a new planet, not an adjustment to Newton's laws, but a completely different way of thinking about space and time and gravity. So So in 1915, after a decade of thinking, scribbling, doubting, and walking around Prague looking like a distracted genius, Einstein published his theory of general relativity. And in it, he said this: mass bends space-time, and that's what we feel as gravity. It's just the result of trying to move through that bent geometry. In Einstein's world, the Earth doesn't orbit the sun because the sun pulls it. The Earth moves in a straight line, but that line is curved because space-time itself is curved. Imagine putting a bowling ball on a trampoline and then rolling a marble nearby. The marble curves not because it's being pulled, but because the trampoline itself is warped. That's gravity. Except the trampoline is four-dimensional space-time and the marble, is a planet. When Einstein ran the numbers in 1915, he calculated how much extra precession his theory predicted. The answer? 43 arcseconds per century, exactly the value that had stumped Newtonian gravity for over 200 years. It wasn't just close, it was perfect. Einstein reportedly said he felt his heart race when he saw the results. Mercury's orbit had quietly been proving him right for centuries, and all it took to notice was throwing out everything we knew about space and time. Mercury wasn't just a rock circling the Earth, it was a stress test, an early crack in the facade of classical physics. Most people ignored it. Einstein didn't. He listened to what Mercury was whispering, and in doing so, he changed the way we think about the universe. That's the thing about physics. The truth often starts with something small. A discrepancy, a leftover, something that doesn't quite fit. Mercury's orbit was off by less than a blink per century, and from that we learned that gravity is not a pull, it's a curve, and we are all falling through it. General relativity explained a lot of things, like why Mercury's orbit was slightly off, why light bends around stars, and eventually why black holes exist. But the theory also had a side effect, and that side effect was weird. In 1916, Einstein ran the math, and he found something strange hiding in his own equations. He saw that if you shook a massive object hard enough, like smashing stars together, you'd send ripples through space-time, actual waves, stretching and squeezing space itself. He called them gravitational waves. And just like that, the quiet fabric of the universe got noisier. But there was a catch. These waves were tiny, not like a grain of sand. They were small, like less than the diameter of a proton, across kilometers. That's not a ripple, it's a cosmic joke. Einstein thought they were real, sometimes. Then he thought they weren't, then he thought they were again. Then he co-authored a paper with Nathan Rosen that claimed they didn't exist, which was rejected by a journal, so he revised it and changed his mind again. This went on for decades, and in the meantime, physicists argue. Are gravitational waves real, or are they just math with good PR? One camp said yes, another said no. Most people said we don't have the technology to find out anyways. And for a while, the idea just kind of floated there. Cool but irrelevant, like flying cars or string theory. Then along came Joseph Weber, the guy from before, the one with the aluminum cylinder. He didn't care about the debates. He wasn't chasing Nobel Prizes. He just wanted to see if Einstein's ripples were out there, and if he could build a machine to hear them. So this is what Joe built. It's called a resonant bar. It was about 2 meters long, weighed several tons, and it sat really, really still all the time, which is exactly what you want from a machine that's supposed to hear the tiniest distortions in the universe. He believed if a gravitational wave passed through Earth, like say from 2 black holes colliding over 1 billion light years away, it would stretch the bar ever so slightly, like by a fraction of a proton, and this bar would ring, not enough to hear, but enough to record, maybe. Now imagine trying to hear a sound that quiet in the 1960s, the same decade that brought us lava lamps, Led Zeppelin, and the Ford Pinto. This is the scientific equivalent of trying to photograph an atom using a potato. But Joe did it anyway, because Joe believed, and because no one else was trying. In 1969, Joe announced that he'd heard something. The press went wild. The New York Times called it a scientific revolution. People started talking about Nobel Prizes. In science, the hardest part isn't making a discovery, it's convincing the rest of the world that it's real. Joseph Weber had thought he had done both, By 1969, he had published multiple papers claiming to have detected gravitational waves multiple times. He had two resonant bar detectors spaced far apart, and his results showed near simultaneous results. He wasn't just excited, he was certain. But here's a rule in physics. 1 detection is an anomaly, 2 is a coincidence, and 3 is still not enough. And 4 better be repeatable. The scientific community had questions. If Joseph Weber had detected gravitational waves, other people should have seen them too. So they built bars, calibrated them, tuned them to resonate just like his. They waited, and nothing came. In Munich, in Glasgow, in Stanford, no waves, no hum, just static. Weber's colleagues grew frustrated. They couldn't replicate his results. They couldn't even find the patterns he was pointing to, and when they looked closely at his methods, they saw issues. His analysis was unorthodox, his thresholds for signal were low, he sometimes interpreted ambiguous noise as meaningful events. To his critics, it looked like cherry picking. To his defenders, it was creative interpretation. To Weber, it was data. But physics doesn't care about creative interpretation. Physics wants confidence, replication, margins of error, control for noise, control for human bias. Weber's data didn't meet the bar. Pun unfortunately intended. Weber didn't back down. He insisted his bars were working. He pointed out how sensitive the setup was, how easy it was for others to miss a signal if their calibration was off by even a little. He accused the community of groupthink, of ignoring evidence because they didn't like the implication. In private, he grew bitter. In public, more defiant. He published more papers, claimed more detections, but with each new claim, the distance between him and the rest of the field widened. By the mid-70s, gravitational wave research had mostly abandoned the bar. The community was moving on to new methods: cryogenic suspensions, superconducting detectors, and laser interferometers. Weber's name stopped appearing in citations, his lab fell quiet, and funding dried up, and the Nobel buzz disappeared. Weber's results weren't fake, though, not in the malicious sense. He didn't fabricate data, he didn't alter numbers, he truly believed he had heard something. But belief isn't peer review, and in the end, what he detected wasn't gravitational waves, it was noise. Earthquakes, trucks, temperature fluctuations, and a healthy dose of pattern seeking. And here's the part that's difficult to explain. Weber wasn't a crank. He was a Navy radar expert, a respected physicist, a teacher. He had tenure, awards, invitations to speak at the most prestigious universities. But science is not a story about who you are, it's about what your data can prove. And the more Weber believed he had found the signal, the more he stopped looking for reasons he might be wrong. Joseph Weber didn't live to see gravitational waves confirmed, but in a strange way, he had heard them anyway. Not through aluminum bars, but through something else. A machine hundreds of times more sensitive, stretched across kilometers, built with mirrors and lasers and silence. The torch had passed to a new generation, to a new idea, to a machine called LIGO. But that's another story, and it starts, like all others, with someone asking, what if we could listen to the universe itself whisper its secrets?